Hello everyone. So in this video, we will see what is traveling salesman problem and how to formulate traveling salesman problem in LPP. So traveling salesman problem is a very standard problem where there is a salesman who is located in one of the cities and he has to visit all other cities and come back to his home city. So the goal is to visit all cities once and return to the starting city with minimum total distance, time or cost. So it is widely used to model delivery routes, field service trips, inspection rounds, and logistics planning. Even with small increase in cities, the number of possible routes grow very fast. So smart algorithm solvers are needed. Excel solver can handle small TSP instance like 4 to 10 cities for classroom demonstration and practice. Okay, so in this example, we will take 4 cities A, B, C, and D, and the salesman is situated in the city A. So I have shown 4 cities A, B, C, D, which is also called 1, 2, 3, 4, and a distance matrix has been given. So distance matrix is a matrix which shows the distance between individual cities. So you can see distance between the diagonal elements are 0 because distance between two same cities are always 0. Now the first thing that comes to our mind is, can we check all the routes and figure out which is the minimum distance? Yes, we can do so for smaller problem instance. Like in this case, there are 4 cities, so number of routes will be 4 minus 1 factorial, which is 6. So you can see I have written down all the 6 nodes and I have calculated the distance for all the nodes. And after calculating the distance, you can see the distance for the first route is the minimum, which is 20. So the optimal answer for this problem is 20. Now in the next slide, we will see how to actually solve this without enumeration and formulating as a LPP and solving it. Okay, so this is the formulation for the traveling salesman problem. So for all the sets we have, for all the cities we have taken set n is 1, 2, 3, 4. So decision variables we have taken as xij. So xij is equal to 1 if the tour goes from node I to node j. So if the salesperson is going from I to j, the value of xij will be 1, otherwise it will be 0. So objective function is minimization of the total distance. So what they have done, they have multiplied the distance matrix with all the decision variables. So wherever it is 1, the distance will be incorporated and added. The constraints, there are 3 constraints. So the first set of constraints is for all the nodes. Exactly one outgoing arc should be from there. So if the nodes are 1, 2, 3, 4, like from 2 only one route should go out. So this is what is meant from for the first constraint, and this is applicable for all the cities. Similarly, the constraint 2 says that for any city, one incoming arc should be there. So as you can see in city 3, only one incoming will come from 2. It cannot happen that it is coming from 2 also, it is coming from 4 also. And no self loops are allowed. You cannot have x2 2 is equal to 1 because the salesperson will not travel from 2 to 2. That is logically incorrect. So we'll have to make sure that these variables are equal to 1. And we have to make sure that the decision variables are binary. So this is how you define the variables. And let's see what is the solution we are going to get if you run this LPP by coding in Python or any other language. So when you run the program, you see this is the solution we get. X14 is 1, X23 is 1, X32 is 1, and X41 is 1. When you check the roots for all the 4 cases, you see it forms 2 cycles. The first is 1 to 4, 4 to 1. X4 is 1. So from 1 you reach 4, and then 4 you reach 1 again. Similarly 2 to 3 and 3 to 2. So this is the solution we have got, which is actually 2 tours, but this solution is not acceptable. So this is the problem which is called subtour problem in a traveling salesman problem. So now we need to put additional constraints for this subtour elimination. Otherwise, this solution is not an acceptable solution. So here you can see we have put one additional solution that if a situation happens, if x14 is 1, then x141 cannot become 1. So this is what we have put, that if you have gone to any city, you cannot immediately come back to the home city. So this is what has been put by the constraint as shown shaded in yellow. And this has to be put for all the nodes. When you run this program, you get the solution which is shown in the next line. So here you can see the solution is acceptable. It forms a node and the total distance is 20. But we have already seen using enumeration. That means this solution works. So this method works and this is called subtool elimination. But there is a catch. Let's see if the number of cities or nodes is even more than 4. If the number of cities is, let's say, 6, again we are going to have a problem. As you can see, it can go from 1 to 2, 2 to 3, and then 3 to 1, 4 to 5, 5 to 6, and then 6 to 4. Again, the problem of subtool is coming. The additional constraint that we had just put is not working in these type of cases. So what we need is, we need an additional, a generic constraint which will eliminate the subtool, be any type of nodes, be it any number of nodes. So we'll see the generic formulation in next week. Yeah, thank you.